What happens when you cross the event horizon? Does it disappear forever? Or is there something else, a place where the laws of the universe stop making sense? This question has intrigued scientists and fascinated the cosmos since black holes were first theorized. When we think of these giants of the universe, they seem both destructive and mysterious, places where space and time literally curve to infinity. For a long time, black holes were treated as mere cosmic abysses, places from which not even light, the fastest thing in the universe, could escape. However, discoveries in recent years have completely changed this view. Today, we know that they can be much more than just gravitational tombs. They can be portals to new dimensions, extreme energy factories, or even the answers to the biggest questions in modern physics. Do black holes hold secrets about the beginnings of the universe? Are they portals to other worlds, or just islands of total destruction? And, above all, what do black holes tell us about the fate of everything we know? Today, we're going to unravel these mysteries and explore what's literally beyond the horizon. Black holes are, at the same time, the simplest and most complex objects in the known universe. They are defined by just three fundamental characteristics: mass, rotation, and electrical charge. And yet, within this simplicity, they hide a mystery so profound that it challenges our understanding of physics, space, and time. At the heart of these mysterious celestial bodies is the concept of singularity, a point where the laws of physics as we know them cease to operate. This is where gravity is so strong that space and time merge, creating a place where density tends to infinity. But what is really there is the singularity, the end point, where all matter is destroyed. Or is this just our lack of understanding about what really happens beyond the event horizon? If we want to understand a black hole, we must start with what defines it: the event horizon. This is the frontier of no return, a region where gravity is so intense that not even light can escape. Once anything, matter, light, or even information crosses this threshold, it is lost forever. At least from the perspective of those on the outside. But what happens inside the event horizon? This is where science begins to run into its own limits. According to Einstein's theory of general relativity, time and space behave in strange ways near the event horizon. To an outside observer, for example, someone approaching a black hole would appear to slow down until they eventually come to a complete stop, frozen in time. This fascinating phenomenon, known as time dilation, reminds us that the gravity of black holes not only warps space, but also the flow of time itself. However, from the point of view of those who fall into the black hole, the story is different. The person, or object, would cross the event horizon without noticing anything extraordinary at the time. The problem? There is no way for her to report what she saw or experienced inside. It is as if nature has placed an impenetrable veil over these cosmic ABYSSES. At the center of a black hole lies the singularity, a point of infinite density, where gravity becomes so strong that all known laws of physics break. The theory of general relativity describes the singularity as the final collapse of all the matter and energy that was sucked into the black hole. But this idea is not without problems. Modern physics faces a fundamental paradox when dealing with singularities. While general relativity predicts its existence, quantum mechanics that describes the behavior of particles on a subatomic scale suggests that something more complex and unknown must be happening. The unification of these two major areas, general relativity and quantum mechanics, is one of the biggest challenges in modern physics, and black holes could be the key to solving this enigma. Some theories suggest that the singularity is not the end of the line. Instead, it could be a portal to another universe, where everything that was sucked into the black hole emerges into a new reality. Other physicists conjecture that singularities could be points connected by wormholes, creating shortcuts in space-time. These ideas, while still speculative, point to the possibility that black holes are more than just places of destruction. Today we know that black holes come in different sizes and shapes. They generally form in two main ways. Stellar black holes, formed by the collapse of massive stars at the end of their lives. These black holes have masses between 3 and 100 times that of our Sun. They are relatively common in the cosmos and are found in many galaxies. Supermassive black holes. These cosmic monsters occupy the centers of the largest galaxies, including the Milky Way, with masses reaching millions or billions of times that of the Sun. Their origin is still a mystery, but it is known that they play a crucial role in the formation and evolution of galaxies. Despite decades of studies, there is a lot we still don't know. For example, micro-black holes, theorized by particle physics, would be the size of an atom, but with a mass comparable to a mountain. Would they be possible? And if so, could they be used, theoretically, as infinite sources of energy? Another mystery involves the behavior of information in black holes. When something falls into a black hole, what happens to the information about that object? Today's physics faces a paradox. General relativity suggests that all information is destroyed, while quantum mechanics states that this is impossible, as information must be preserved in the universe. This dilemma, known as the information paradox, is one of the great problems that physicists like Stephen Hawking have tried to solve. The possibility of black holes being portals to the unknown is not as absurd as it seems at first glance. The theory of general relativity allows for the existence of wormholes, hypothetical bridges that connect different points in space and time. Some theories suggest that black holes could be connected to these wormholes, functioning as entrances or exits. More impressively, some scientists, such as theoretical physicist Kip Thorne, speculate that wormholes could be used for time travel, although they would require conditions of energy and stability that are still beyond the reach of our technology. Others, like Leonard Susskind, theorize that black holes could be connected to parallel universes, opening up the intriguing possibility that what falls into one black hole in our universe could emerge as matter in another dot. Despite all the mystery that black holes still carry, they have already taught us a lot about the cosmos and its fundamental laws. They validated theories once considered abstract, such as general relativity, and provided crucial insights into high-energy physics. Most impressively, with the first direct image of a black hole captured in 2019 by the Event Horizon Telescope, we literally saw the shadow of a black hole for the first time, a historic achievement and a reminder that science continues to break barriers. Black holes fascinate scientists and onlookers around the world today, but it wasn't always this way. For a long time, they existed only as a theoretical idea, a product of mathematical equations that challenged the understanding of reality. The journey to understand these cosmic monsters goes back centuries and involves some of the greatest minds in science. Despite this, the idea was initially met with skepticism and disdain, until technological and observational advances proved that these objects not only existed, but also played a crucial role in the architecture of the cosmos. The idea of cosmic objects with gravity so intense that not even light could escape was first proposed in the late 18th century. Two scientists, independently of each other, suggested something similar to what we now call black holes. John Mitchell, a British clergyman, and Pierre-Simon Laplace, a French mathematician and astronomer. John Mitchell published a paper in 1783 in which he described an object so massive that its gravity would prevent even light from escaping. He called it the dark star. At the time, the idea was purely hypothetical, as light was still seen as a stream of particles, and the tools to test this hypothesis did not exist. Pierre-Simon Laplace reached similar conclusions using Isaac Newton's principles of gravity. He introduced the concept in his book Exposition du Monde, but curiously withdrew the idea in later editions, perhaps due to the perception that it was scientifically fanciful. These early works planted the seed, but it would be centuries before science could seriously address such objects. The next major breakthrough came in 1915, when Albert Einstein introduced his theory of general relativity. This theory revolutionized our understanding of space, time, and gravity. With general relativity, space was no longer seen as a static, unchanging backdrop where events take place. Instead, it was described as something dynamic and flexible, which bends in response to matter and energy. Shortly afterwards, in 1916, German physicist Karl Schwarzschild found a mathematical solution to Einstein's equations, which described a point of gravity so intense that nothing could escape. This point became the theoretical basis for the modern concept of black holes. The Schwarzschild radius, now known as the event horizon, describes the distance around that point at which gravity becomes inescapable. Schwarzschild, however, never lived to see his discovery gain traction. He died the same year, during the First World War. Interestingly, even Einstein initially rejected the idea that black holes could actually exist in nature. He believed that this type of extreme gravitational collapse was a mathematical anomaly, not something observable in the cosmos. Although the theory was present. It was in the 1930s that science began to consider the idea of black holes more seriously. This happened due to advances in understanding massive stars and their final stages of life. Two physicists, Robert Oppenheimer, famous for his role in the Manhattan Project, and Hartland Snyder, published a revolutionary paper in 1939 describing how very massive stars could collapse under their own gravity at the end of their lives, creating what was then called a frozen star. This work provided a physical model for stellar black holes, showing that they could indeed form in nature. Despite this, the scientific community still remained skeptical. The idea of black holes seemed too strange, and many believed that some unknown mechanism in physics would prevent complete collapse. 1960s and 1970s. The golden age of black holeset. Was in the 1960s and 1970s that black holes went from a fringe concept to one of the most fascinating topics in astrophysics. This happened thanks to a combination of technological advances, new theoretical models, and observational discoveries. Physicist John Archibald Wheeler not only helped popularize the idea of black holes, but also coined the term we use today. Before that, the objects were called gravitational collapses, or shrunken stars, terms that did not capture the true nature of these phenomena. The introduction of the name black hole gave the concept a clarity and mystique that attracted the attention of the public and the scientific community. In the 1970s, Stephen Hawking made a surprising discovery. Black holes were not completely black. They emitted faint radiation, today called Hawking radiation. Due to the effects of quantum mechanics near the event horizon, this challenged the view that black holes were merely pits of destruction, and proposed that they could evaporate over billions of years. His discovery opened a bridge between general relativity and quantum mechanics. Although many questions still remain unanswered, during this time, X-ray telescopes detected sources of radiation associated with what we now know to be stellar black holes. One of the first confirmed candidates was Cygnus X1, a binary star where one of the components appeared to be a black hole, despite decades of research. It was only in 2019 that we got the first real image of a black hole. Thanks to the International Event Horizon Telescope (EHT) project, the target was the supermassive black hole at the center of the galaxy M87. Located about 55 million light-years away, the image showed the black hole's famous shadow against a glowing ring of hot gas, an elegant visual confirmation of theoretical predictions. This revolutionary milestone solidified black holes as a real element of the cosmos, and opened new doors to study them more deeply. Over the centuries, Black holes have evolved from a fringe idea to a mainstay of modern astrophysics. Today, they are studied not just as destructive objects, but as natural laboratories that allow us to explore the fundamental laws of the universe, from general relativity to quantum mechanics. More impressively, they have had a lasting impact on our culture, inspiring works of science fiction, films like Interstellar, and even metaphors about the unpredictability of existence. Black holes, once seen as mere theoretical speculations, have come to play a central role in modern science with the advent of advanced technologies and global scientific collaborations. The last 50 years have marked a veritable rise in the study of these cosmic giants, with discoveries that have challenged our conventional understanding of physics and revealed the astonishing complexity of the universe. Before we could directly observe black holes, our first clues to their presence came from their gravitational effects on surrounding objects or the emission of radiation at specific wavelengths, such as X-rays. In the 1960s, with the introduction of telescopes sensitive to X-rays, scientists began to identify high-energy sources that could be associated with black holes. One of the most famous discoveries was Cygnus X1, a binary star where there appeared to be a black hole sucking matter from its companion star. This system generated an intense glow in X-rays, providing indirect evidence of the existence of stellar black holes. One of the biggest revolutions in the study of black holes occurred in 2015, when LIGO Laser Interferometer Gravitational Wave Observatory detected, for the first time, gravitational waves. These ripples in the fabric of space-time were produced by the collision and merger of two massive black holes. This discovery was historic. It not only confirmed predictions of Einstein's theory of general relativity, but also opened up a new way of studying the cosmos. Since then, several other black hole mergers have been detected, allowing scientists to analyze their sizes, masses, and distances. Until 2019, our visual understanding of black holes was based exclusively on computer simulations and theoretical concepts. Everything changed when the Global Event Horizon Telescope (EHT) collaboration managed to capture the first image of a black hole, the supermassive black hole at the center of the galaxy M87. The EHT is, in fact, a network of telescopes positioned in different parts of the world, from the South Pole to the Atacama Desert in Chile. Using a technique known as Very Long Base Interferometry, VLBI, scientists combine data from all these telescopes to create an Earth-sized virtual telescope. The result was unprecedented resolution, enough to visualize the disk of gas around the black hole's event horizon. The resulting image, a bright ring with a shadow in the center, was direct visual proof that black holes really exist. This milestone in science was considered so important that the EHT project received prestigious awards and global recognition. Although we haven't yet directly seen the inside of a black hole, we have theories that have advanced our understanding of what might be happening inside. One of the biggest advances in this regard was the discovery of Hawking radiation. Stephen Hawking, in the 1970s, proposed that black holes are not completely black, and that they actually emit subatomic particles in the form of radiation. This phenomenon occurs due to quantum fluctuations at the edge of the event horizon. Most impressively, due to this slow loss of energy, black holes could eventually evaporate over billions of years. This discovery was revolutionary because it seemed to violate the idea of black holes as eternal abysses, from which nothing can escape. Furthermore, it brought problems to the current model of physics, generating the famous information paradox. If black holes evaporate and disappear, what happens to the information about what was sucked into them? The search for answers continues to challenge physicists to this day, while we study giant black holes in distant galaxies. Some scientists speculate about the possibility of creating or detecting micro-black holes here on Earth. One of the tools used in this search is the Large Hadron Collider, LHC, the largest particle accelerator in the world. Located in Switzerland, the LHC is capable of recreating conditions similar to those that existed shortly after the Big Bang, generating gravitational collapses on a much smaller scale. This raised the possibility that small black holes could be created at these very high energies. So far, no mini black holes have been detected, but the search continues. If micro black holes are observed, it could revolutionize not only the study of gravity, but also our understanding of string theory, as these small objects could reveal unique properties of the additional dimensions proposed by this theory. Another landmark advance involves observations of the black hole at the heart of our own galaxy, the Milky Way, known as Sagittarius A*. This supermassive black hole has a mass equivalent to about 4 million suns. Radio probes and telescopes, such as the Very Large Array, VLA, have allowed astronomers to map the orbits of stars around Sagittarius A*, by studying how these stars move at extreme speeds close to the galactic center. We confirm that there is an incredibly massive and compact object there, a black hole. This discovery not only validated theories about supermassive black holes, but also raised many questions. For example, how did they form? Did all supermassive black holes originate from smaller mergers, or do they have a completely different formation process? Supercomputers play a crucial role in the study of black holes. Simulations of black hole collisions, the behavior of matter in the accretion disk, and space-time deformations help us refine our models. These simulations revealed surprising details, such as jets of plasma launched at speeds close to that of light, a phenomenon often observed around active black holes. These relativistic jets can travel thousands of light years and influence the entire galaxy around them, showing that black holes are much more than cosmic vacuum cleaners. Advances in the study of black holes have not occurred in isolation from the rest of science and society. They inspired new technologies in communications, such as interferometry, and challenged our philosophical paradigms about the universe. From a technological perspective, the challenges of observing black holes have inspired innovations in telescopes and data processing. From an existential perspective, black holes continue to provoke questions such as, what happens to time inside a black hole? Do they keep secrets about the beginning of the universe, or even about its end? Advances in this area demonstrate that black holes are much more than passive objects in the cosmos. They are engines of cosmic transformation and windows that connect us to the deepest questions of existence. Success after success. Creativity and global collaboration have shaped what we know and what we are still discovering, despite being in the scientific community's spotlight and captivating curious minds. Around the world, black holes are also a constant source of controversy, theoretical conflict, and experimental frustration. Behind the glamorous advances and bold discoveries lies a field full of challenges, where ideas are contested and paradoxes remain unresolved. Black holes have taken us to the limit of science, and we still don't know if we will be able to overcome it. One of the most controversial issues related to black holes is the information paradox, a dilemma that has divided the brightest minds in modern physics, such as Stephen Hawking, Leonard Susskind, and Gerard T. Hooft. This paradox arises from the conflict between two of the most fundamental theories in science: Einstein's theory of general relativity, which describes the behavior of gravity and predicts that everything that crosses the event horizon of a black hole is swallowed by the singularity at the center. This theory is not concerned with the fate of the information that defines an object, such as its quantum properties. Quantum mechanics, on the other hand, states that information in the universe must be preserved. In other words, even if something is destroyed, traces of its fundamental properties must continue to exist. The paradox occurs because black holes appear to destroy information about what goes into them. This violates quantum mechanics and creates a serious problem. Two of the most successful theories in physics come into apparent contradiction. Stephen Hawking at first suggested that information was actually lost inside black holes, something that contradicted quantum mechanics. His statement sparked a huge debate for decades. Years later, Hawking reversed his position, proposing that information could escape in the form of Hawking radiation, albeit corrupted or unrecognizable. Still, the issue is far from being resolved, and many physicists consider the paradox a crucial question for the unification of quantum and gravitational theories. Are black holes real or just math? Frequent criticism of the study of black holes comes from those who question their very existence. Before the advent of direct observations, such as the image taken by the Event Horizon Telescope, many scientists viewed black holes as a purely theoretical concept, mathematical solution that may never be confirmed in practical reality. These criticisms resurface in discussions about event horizons. Theoretical physicist Eric Verland, for example, proposed that what we perceive as the gravity of black holes could be explained by as yet unknown laws of nature, without the need for singularities. Other theories, such as the fuzzballs proposed in string theory, suggest that black holes may not have the kind of event horizon we imagine, but rather are densely packed bubbles of energy and matter. The challenge here is not so much skepticism about science, but the limitations of how black holes can be measured and understood. One of the biggest practical difficulties when dealing with black holes is that they are incredibly far from us and hidden by immense amounts of matter and gas. This means that many of our conclusions depend on mathematical hypotheses, whether in general relativity or supercomputer simulations. Much of our understanding of black holes depends on the accuracy of our models. Theoretical models and simulations are invaluable tools, but what happens if these models are wrong? An important example is the concept of singularity. This idea, derived from Einstein's equations, may not be an accurate description of reality. Some alternative theories suggest that the singularity at the center of a black hole could be replaced by something even more exotic, such as a nucleus with not yet understood quantum properties. This would imply that our current models could be distorting reality under certain extreme conditions. Furthermore, although the Event Horizon Telescope was an impressive achievement, the image obtained is actually a reconstruction based on data that must be interpreted by complex algorithms. This inevitably raises questions about to what extent we are actually seeing a black hole, or just a reflection of our mathematical modeling. Although black holes are a seemingly neutral object of study, research associated with them also raises ethical and philosophical questions. For example, projects like LIGO, the Event Horizon Telescope, and the Large Hadron Collider cost billions of dollars and involve global efforts. This raises the question, is it worth spending so many resources to study distant phenomena, while there are pressing problems on Earth, such as climate crises and social inequalities? The study of black holes is undeniably important for scientific progress, but not everyone agrees that it should be a priority. If we are one day able to fully understand how black holes work, we will also be tempted to interact with them. For example, would it be possible to use energy from black hole accretion disks as an energy source for advanced civilizations? This raises ethical questions about the impact on the cosmic balance. Would it be safe or morally acceptable to interfere with these phenomena? As with any scientific field, the journey to understanding black holes has not been without errors and miscommunication. Some notable examples include Einstein's initial rejection. Despite being the creator of general relativity, Einstein rejected, for much of his life, the idea that black holes could physically exist. He believed that some physical phenomenon or mechanism would prevent total stellar collapse. Today, we know he was wrong. The black hole, in pop culture. While science fiction has helped popularize black holes, it has also contributed to the spread of myths. Many works portray black holes exclusively as portals or cosmic vacuum cleaners, distorting their true complexity. Despite controversies, errors, and limitations, black hole science continues to advance. For many brilliant minds, it is precisely in these discrepancies and paradoxes that opportunity lies, resolving the contradictions between quantum and relativity, understanding event horizons, or deciphering the secrets of the singularity are challenges that will guide the next decades of research. Like all science in the making, questions about black holes remind us that progress is an ongoing process full of disputes, revisions, and new interpretations. And even with the difficulties, black holes put us in touch with the enormous human potential to explore the cosmos and ourselves. Black holes, these giants of the cosmos, are not just physical entities. They are symbols of our eternal curiosity. From John Mitchell imagining dark stars in the 18th century to the global collaboration that brought us the first images of the event horizon, black holes challenge us to push the limits of human knowledge, even into the deep unknown. At their core, black holes represent more than the outer reaches of the physical universe. They are a reflection of our own existence and how we approach mystery and complexity. If there is one thing that we have defined throughout the history of the study of black holes, it is that the road to discovering them is as important as the destination itself. What we have learned so far transcends science and leads us to question the cosmos and our place within it. Few cosmic phenomena encapsulate the spirit of scientific progress as well as black holes. They began as theoretical curiosities, mathematical predictions that seemed too absurd to correspond to the reality of the universe. Even the most renowned scientists have rejected their existence, seeing them as mathematical aberrations that could not exist in practice. But science, with its unique ability to reconsider and reinvent itself, has led us to increasingly convincing evidence. Each advance in work from Schwarzschild and Penrose to Hawkins, from the gravitational waves detected by LIGO to the Event Horizon Telescope image, shows that human understanding is a layered construct. Black holes, finally, teach us that curiosity, combined with the scientific method, can lead us to uncover even the greatest mysteries of the universe. They also show us that science thrives, not because we have all the answers, but because we have the tools and courage to ask questions. Black holes are also a mirror to humanity of our way of understanding time, space, and, above all, although they are incredibly distant and exotic structures, they also evoke profound reflections on what it means to be mortal in a vast and sometimes incomprehensible universe. Think about the concept of an event horizon. It is not just the physical boundary beyond which nothing can escape. It's also a powerful metaphor for our own limits. Just as we cannot see what lies beyond the event horizon, there are aspects of life, time, and the universe that we may never fully understand. And yet we keep trying to look beyond. Black holes challenge our notion of time, where a singular point can encapsulate the history of the universe. They show us that reality is stranger than we imagine, and perhaps even stranger than we are capable of imagining. More than any other phenomenon, black holes test the limits of what we think we know. They force us to question some of our most deeply held beliefs about reality. They challenge the idea that time always flows linearly, that space is continuous, that information never disappears. They force us to accept that there are places where our laws of physics, the very laws that govern our everyday lives, simply do not apply. These contradictions have implications that reach beyond the cosmos. As we face the mysteries of black holes, we also face fundamental questions about ourselves. How do we deal with the unknown? How do we reconcile our search for certainty with the inherent uncertainty of the universe? And finally, how do we live our lives knowing that we are just a small part of something much bigger, something we may never fully understand. In addition to their undeniable contribution to science, black holes have an appeal that transcends the academic world. They have a powerful influence on pop culture, inspiring films like Interstellar, series like Doctor Who, and even music and video games. They are gateways to science, awakening the curiosity of millions of people who may never have been interested in physics or astronomy before. But what makes black holes so fascinating to the public? Maybe it's the fact that they represent absolute extremes of density, of gravity, of mystery. Or maybe it's because, in some way, they capture the drama of existence itself. What is taken from us, what collapses, and what can emerge into the unknown. Black holes remind us that we are part of something much bigger. They invite us to contemplate the vastness of the universe, not with fear, but with a sense of wonder and curiosity. Despite impressive advances, we have barely scratched the surface in understanding black holes. The information paradox still persists. The nature of the singularity is still misunderstood, and the fusion between general relativity and quantum mechanics is still a puzzle. Black holes represent the final frontier of our scientific understanding, and possibly the key to discovering a unified theory of the universe. In the future, space missions will be able to explore extreme gravitational phenomena in greater detail. New technologies, such as telescopes with greater range and precision, will allow us to observe black holes with an unprecedented degree of clarity. But perhaps the greatest legacy of black holes is not what they teach us about the cosmos, but about ourselves. Because in the end, they inspire us to explore. They remind us that we are dreamers and questioners, navigating a small blue dot in a vast, unpredictable universe. Black holes are, in many ways, a metaphor for science itself, journey into the unknown. Guided by the desire to understand the incomprehensible, they show us that the pursuit of knowledge is never a straight line, and that often the greatest revelations come from confronting our flaws, paradoxes, and limitations. In the infinite universe, black holes remind us that, as humans, we will never be content with just observing the stars. We will always look beyond them, asking, what next?